then the big button is
What's that
forward. Big button is forward,
Yeah.
and then the top button, if you press and hold, you can also see on the screen there. It's red.
Tell me again.
Top button, press and hold.
Top button, press and hold.
Big button is the advanced.
Oh, okay, okay.
You don't have to point it anywhere in particular. Just, it knows.
Is it? I think it's not really a big rock here.
Oh no. It's,
Okay, our final speaker for today is Anand Pillay, speaking about pseudofinite fields and combinatorics.
Yeah, I'm not sure everybody's here. Is Rahim here, for example?
Let me ring the bell.
Yeah. Hmm? No, just, I mean, I'm not, I mean, usually there's a bell normally, you know, so. Everybody here? Everybody you sing comfortably? Okay, all right. So just thanks to the organizers for inviting me and for organizing this day for Zoe, and to recognize Zoe, remember Zoe, and yeah, so I did. I wrote Zoe died in January. I wasn't there. I saw her last time in Lumini, which in fact I gave a talk on the same topic there, and yeah, I wrote a kind of an in memoriam, not exactly an obituary, an in memoriam in the Notre Dame Journal of Formal Logic, which I'm an editor of. So I just did it, and there is something, a couple of pages. You can probably see it online. Notre Dame Journal of Formal Logic and Zoe, and so I'm not going to repeat that, except that I met Zoe a long time ago, 1978. We met Zoe when I went to Paris as a postdoc, and we've known Zoe since then. Got very close. So yeah, so in Paris, I was there a couple of years, and Zoe went to America, right? Went to Yale, and the first couple of years, it was, to be frank, everybody was in love with Zoe, of all persuasions, people of all persuasions. And you meet someone in the bar, they talk to them, and they say, "You too?" It's true story. And then what? Yeah. And we spent actually Fields Institute is an important place where we spent time. So there was a program in the 90s, and also with Zoe, we were very close, but with relationships goes up and down. As with every, it's not. We're close, and that closeness meant that things were not always so smooth. But we had a very nice, in 96, there was a program, in 96, 97, there was they called it algebraic model theory. It was the program, a year program. First semester was model theory, second semester was kind of universal algebra. And I was here all the time, and Zoe was here. And who else was around? Brad was here all the time. We did things with Brad. Is Brad here, by the way? Yeah, we did some important things. Anyway, but we spent a lot of time with Zoe. We shared a lot of things, and including getting food poisoning in a late night Indian restaurant somewhere. And anyway, so and then in 21, there was another 4 years ago. Fred was also here. Anyway, that time we spent a lot of time together, and it was very so. We miss her very much. I'll talk about pseudofinite fields, something which Zoe actually worked on, and so I'll mention Zoe again. Just one final thing I want to say, which maybe is a bit delicate, but Zoe had a social conscience. She wasn't scared of speaking out about things. Brad reminded us, just me at lunchtime, that when was it? Ali Nessin went back from, at some point in the 90s, he went back to Turkey, and no, 80s, Turkey, got arrested, correct? He did military service and got put in prison, and so he was very active around that. She was active about other things, about Tuna, the Turkish. She was outspoken, and so I just want to say that. And I suppose, bearing that in mind, bearing also in mind that Deirdre on Monday, was introduced, talked about this being the land of certain indigenous people, and which represents, I know it's now common in Canada to say this, but it represents some recognition of an historic injustice, namely the injustice of genocide, dispossession, ethnic cleansing. So bearing this in mind, it would be irresponsible of me, not anybody else, not to mention what's going on in the Palestinians, which is exactly the same thing. It's dispossession, genocide, ethnic cleansing by Israel with the support of the US, right? And if you talk about the past, why not the present? Which is more important. Everything's important, but you should see what's going on now. And there's a war now with Iran. And I think it'll be a cover to complete the job with the support of the US. So unfortunately, people would say never again, but things are repeated. And this is something that I know Zoe was very concerned about, right, too. That's what I want to say to begin with. And the topic is pseudo-finite fields and combinatorics. I joined with Atticus, my student in Notre Dame. I've given this topic, I've talked about this 4 times. This is the last time I'm talking about it, So I talked about 4, actually first was in Lumini, last time I saw Zoe, September. Second time was in Waterloo, October colloquium. UIC, April, logic seminar, all right? And now these are the same topic, but they're different talks, because I don't like repeating myself, except for jokes, of which this is one. Okay, so they're different, but partly because we understood a bit more about connections of what I'm saying with other stuff. We understood a bit more in the past 2 months, so I'll try and. Also, I somehow didn't completely realize that I didn't look at the program so much. So I didn't realize there'd be a lot of people who are not from model theory. So I apologize. At the beginning, there'll be some little bit model theory jargon and notation. So I'll try and explain a little bit what I'm doing. So this is really, this is a bit off the main theme of the meeting. Because the combinatorics, but somebody else is, Marnie's talking about combinatorics and differential transcendence, is that right? So okay, so I think I've 7 minutes I used up already, so good. Right, so the main theorem is a structure theorem, which we call regularity or yeah, okay, I'm going to sit down. Is that okay if I sit down? I may use the board now and then. It's a structure theorem, which we call regularity or quasi-randomness, for pairs consisting of G, a group, D, a subset, uniformly definable in all finite fields, which means there's a collection of formulas in the language of rings, such that if I take these pair of formulas or something like this and plug in take a finite field, plug in some parameters, look at the group and the subset it defines, you get a family of things as the finite field varies and the parameters vary. I call this a uniformly definable collection of pairs. Is that okay? All right. There's other ways of describing it. You can fix a number m and think of a formula, an expression in the language of valued field, in the language of rings, a formula with parameters with at most m symbols. And you call this complexity m. So to have bounded complexity to be uniformly definable is the same thing. Think of it like that if you want. It goes via studying pairs definable in a pseudo-finite field, right? Now, pseudo-finite field, I'll say what I mean in a sec. Pseudo-finite field, you could think of a pseudo-finite field if you want as either something looking like an ultra product of finite fields, or if you have a non-standard analysis kind of, you like non-standard analysis, you could think of it as a finite field in the sense of a non-standard model of set theory, which thinks it's finite. It's a nice way of thinking about it because this model of set theory, it's got a non-standard natural numbers, but it thinks the thing is finite, so everything has got a cardinality, which is a non-standard natural number. You could just do, it's just simple, you can do everything, but it's not really the, you know what I mean? So it's a useful way of thinking about pseudo-finite fields. What happened? What happened? Did I press by mistake? God, I didn't mean to press something. It happens by itself. Okay, sorry. So a model theoretic environment for algebra. So this, what's the connection with this, with the theme of this meeting? Is a model theoretic environment for algebraic dynamics is the theory ACFA of algebraically closed fields with a generic automorphism. Okay, and this is fantastic theory. It's not stable, but it's the theory behind Manning Mumford, behind algebraic, the papers that Notre, is it? Notre, or Notre. That Notre, quoted by Zoe and Ushofsky. Okay, it's all in the context of this theory ACFA. And pseudo-finite fields are exactly the fixed fields of sigma, where K sigma is a model of this theory. Okay? But our results do extend to arbitrary, so our results, you know, the pseudo-finite field business, looking at groups defining pseudo-finite fields, the analog would be looking at a pair GD definable in a model of ACFA, but where the GEDs are finite dimensional in a suitable sense. Anybody define finite dimensional in differential algebra? Anybody define this? Anyway, it doesn't matter. But they do extend to this situation of finite dimensional pairs, GD, defined in a model of ACFA. And in the same way as studying groups in pseudo-finite fields, GD is the same as understanding uniformly definable groups in finite fields. Studying a single pair like this translates into a structure theorem for the collection of finite pairs, GD, defined uniformly in the structure FQ, algebraic closure of finite field FQ, equipped with a Frobenius x to xq, as Q varies. So what I'm saying generalizes to that environment in place of just finite fields, okay? Everything generalized. This goes via Ushofsky's non-standard Frobenius theorem. It says that the theory ACFA is the theory of the non-standard Frobenius. Is exactly the theory of this, of the theory of non-standard models of the collection of all pairs, algebraic closure finite field, power of Frobenius. Okay. Via that, okay. Anyway, understanding the theory of finite fields was one of the big successes of model theory, starting with James Axe. I mean, Axe had this amazing kind of bunch of work. It's very fundamental things that we talk about all the time now. Axe annually. So Axe had this paper on the theory of finite fields, and then Zoe, Van den Dries, Angus MacIntyre studied not just to study definable sets in finite fields, and it means the same kind of thing. You have a finite field, and you have a formula, and change the variables, change the parameters, there is a finite field, what goes on? And this was the theory of finite fields. And there's this very beautiful paper by Chatsidakis, Van den Dries, MacIntyre, and that fed into actually, there's a general theory of so-called, right, so model theory, stable theories are very central. So Dave was talking about omega stable theories. Who else mentioned omega stable? Did somebody else? I did. But Dave was talking about omega stability of differentially closed fields. And there's a generalization of stability to so-called simple theories. And it's also very interesting history connected with actual examples and this understanding of finite fields fed into that general theory, which actually we did just around the time of this Fields program in 96. TPSF is the theory of finite fields plus I'm infinite. So it says I'm an infinite field, but it's a field, so it's a theory, so all the sentence is true in all finite fields. Now you can't say I'm characteristic too, because it's not true in all finite fields, but all things true in all finite fields plus I'm infinite. And by compactness, there are models, okay? It's model complete. Model complete is if I have a pair, one a subfield of the other, then it's elementary substructure. We fix a completion T. This PSF is not a complete theory, but you can control the completions. I want to mention again with Zoe that so Zoe was very working on this stuff at the very beginning, but she also did many survey papers about pseudo-finite fields, and in fact in the program in 2021 there were a bunch of tutorials, and Zoe gave a tutorial on finite fields, pseudo-finite fields. Rahim gave a tutorial, and I gave some lectures, but they appeared actually in a book I wrote last year. But I wrote an introduction, and I'm going to check with Deirdre that volume. What's the status of that volume? Yeah, because I put in some introduction, which is kind of history, a little bit history and. Yeah, I was gonna submit to a volume for Zilber, but I wrote that introduction and I didn't want to repeat myself. But it was, so I hope it comes out soon. But there's the tutorials, which I think is, can I make a little plug? There's Rahim tutorial on differential fields, differential closed fields. There was Zoe on pseudo-finite fields. There was Sylvain Riddle. What was that on valued fields? Important parts of model theory, current model theory, and there was Itai Kaplan about NSOP1, if I'm not mistaken. So it should be a nice volume, should be out. So I look forward to seeing it now. Anyway, we fix a completion T of this theory. M is a model of T, and M bar a saturated model, a big model, universal domain. So these are, okay. In T, in the theory T, so pseudo-finite fields, algebraic closure in the model theoretic sense, which I think was defined, is the same thing as field theoretic algebraic closure. And so really the dimension of a definable set, and in fact, it doesn't have quantified elimination, we have close to quantified elimination. Any definable set is more or less the projection of the F, so let M be a model. So it's a field. It's a projection of the M points of a variety under some finite to one map, a tile map or something. So it's, but anyway, you have dimensions, what we call a geometric structure. I wrote there, which Francois talked about. Now, I'm sorry, the model theory comes in now. There's a notion of dimension. Once you have this, it's like a dimension of So for example, you take a definable set, subset of say M to the N. M is a field. Then its dimension would be the dimension of its Zariski closure, for example. Okay, so you've got dimension of definable sets, and you have a notion of dimension independence. You can also count dimension in other ways in terms of transcendence degree, right? So two tuples are independent over some base set, base field, if the transcendence degree of this and this over that is that plus that transcendence. So in the same way as in field, algebraic closed fields of independence. So you have a notion of independence. Now, sorry for the jargon. It coincides with non-forking independence. T is what we call a super simple theory with rank 1. It just means that the dimension of affine 1 space is 1, as in algebraic geometry. And that's it. And super simple is a slight generalization of stability. So stability, omega stability they've talked about is not omega stable, but it's close in a sense. So this, I'm going to state on the next slide some things with the model theory content. I'm afraid I cannot explain too much about it, but I'll just say these things and maybe I'll say a few words, but the next. So, now look, you think of this M, as a, or MM as a finite field in the sense of a non-standard model of arithmetic, a non-standard model of set theory. So as I said, you have a counting measure, right? In every finite field, you have a counting measure. The measure of a set is how many things are there, right? It's a finite number. And you have in the same way an n star is the non-standard natural numbers. You have an n star valued non-standard counting measure on definable sets, which are like internal sets in this pseudo-finite field. And I call this measure mu star. It's actually, it's not a proper measure, but it's not anything. It's a counting thing with values in the non-standard natural numbers. It doesn't really matter about this, but it does matter, but don't think about it too much. Now, for definable sets, so is the notion of definable set okay with everybody? It's a set. So take a couple of, it lives on n tuples, n space over m. Take a couple of definable sets, D inside U. Okay, let's define a measure, and actually this will now be actually a real valued, a 0, 1 valued measure. Let's call it nu sub u of D. So it's a measure of D, depending on its living inside U, is going to be, look at the mu star of D divided by mu star of U, which will be a non-standard real number between 0 and 1, take the standard part. It's a real number between 0 and 1. Let's call this nu sub U of D. This is the, right, so it's going to be a rational number greater than equal to 0, which is 0 if the dimension of D is too small. So, for example, in a pseudo-finite field, if you take pseudo-finite, look at the multiplicative group and look at the squares. So the squares has measure a half for the obvious, right? So it's exactly that. Not exactly, that's a special case. Are we okay with this measure? So you have a model theoretically, you have a dimension and a measure, these two things together. And you also have definability of dimension and measure, which is part of what's done in Chatzitakis, Van den Dries, McIntyre. And an important fact is that you take, you take a formula. So say phi, x will be a tuple of variables, like this, and take a tuple A, and you take C x bar with a tuple B bar. And you look at a rational number R, and you look at the measure. So you assume X bar is in U, X bar is in U, A bar, B bar, some parameters. You think of this as this will actually be, depending on A, B, will be a formula, definability of measure equals R, is a formula delta AB. So you just say delta XY. This is what's called a stable. This will be a stable formula in the sense of model theory. It means that, what does a stable formula mean? It means that you have delta X bar Y bar in a model, in a structure, defines a kind of bipartite graph. There's the X bar, there's the Y bar, there's the relation delta holds. And it means that that bipartite graph omits the K half graph for some K. The K half graph is the graph. What's the K half graph? Tell me, Jim. What's the K half graph? It's just one. I can't say. Somehow can't say the words. Yeah, K. Yeah, you have 1 to K. 1 to K, and the relation holds in this way, this way, this way, this way, and not other way, right? So stability of a formula dLTXY is the same as stability of the corresponding bipartite graph is omitting as an induced subgraph the K half graph for some K. Okay, and understanding stable formulas is very important in model theory. It's called local stability theory. Okay, I didn't get very far. So now take a group definable. So say a definable group defined, say, in my monster model with parameters from M. First statement, these are the ingredients. G00M equals G0M. Okay, what the hell does it mean, right? So G00M is some kind of definable compactification of G. right? In ordinary mathematics, you have the notion of the Bohr compactification of a group. It's the smallest, it's the largest compact Hausdorff group, such as a homomorphism of your group to him or her with dense image. There's a definable version of this called the definable compactification, and this means that the definable compactification of G is profinite. That's what this statement means. Yeah. So G0 is the profinite compactification. Other one is just compact. So it means that a certain thing is profinite. Now the next thing is a bit delicate. It's the group version of the independence theorem. So I just say this for the model theorist, but this is the model theory in group. So after I do this, I'll pass on to combinatorics. It should be accessible to everybody. This is the only thing which I can't really spend a lot of time. So this is for model theorists. Suppose you have PQR are types over M, focusing on G, of maximal dimension of G. And when you quotient by this definable compactification, the quotient, you get a quotient group. So this is here. So sorry, the compactification is actually the quotient, G mod. That's the definable that's the compactification, the quotient. So when you look in the quotient, which is a group, the compact group, when you take these types in the quotient, P times Q equals R after quotienting. Then you can find realizations A, B, C of PQR independent over the base model such that A times B equals C. This is the group theoretic version of something called the independence theorem, which is a very important theorem in simple theories. Okay, and here's the main lemma, which is behind our results. I'm sorry, right? So suppose you have G, a group G, definable in M, and D in M, both definable. Then there's an M definable normal finite index subgroup H of G, and an M definable set F in subset of G with small dimension, such that this should be M is going to be in, yes, that's right, F in G with dimension. No, F is going to be in G cross G. Sorry, F is in G cross G. So G cross G as dimension, 2-dimension of G with small dimension, such that for all cosets VW of H and G, the value of this measure of the the value of BD intersection CD is constant as this is B times D is the translate of D, C times translate of D by B and by C, is constant for BC in V cross W take away F. That's it. That's the statement. Pardon? Onto what? No, F is small. F is small in, no, I'm not assuming at all this, just as a small, outside of small. So the point is that you look at cosets VW of H and G, then outside a small subset of V cross W, right? You have this constancy of this value of the measure, of the counting measure of BD. So you could think of this. You could think of this as in a finite set. In the finite sense, in the finite context, will tell you the proportion of things in the whole group compared with of the two translates of D by B and by C in the intersection. Okay, it's just this is a key lemma, which is going to be used. Okay, good. Now, from this point, I'm sorry, this point on should be more accessible. So a finite bipartite graph is said to be epsilon regular. We now go to combinatorics. A finite bipartite graph is epsilon regular if for all A subset of V, B subset of W, you can look at the densities of the two. You could look at the densities of the original graph and the graph on AB, the induced graph on vertex sets AB, Density means the ratio between the number of edges and the number of possible edges. Okay, the density, the difference between densities is at most epsilon times that v cross size of b cross w size of a cross b. This is, we call epsilon regular. So this is graph regularity in the sense of Semeredi. So for A, so what it is equivalent to is that for A sufficiently large in the sense of at least as big as epsilon to a third times the size of V, same with B, the difference between the densities, those two densities, is at most epsilon to a third. So it says that sufficient, right, so you can think of this regularity as for sufficiently large subsets of the vertex sets, the densities between the original graph and this and the due subgraph is small. Yep. There's a polynomial equivalent, which I'll give precise numbers, given later about epsilon quasi-random graph due to Chung, Gray, and Wilson in the unipartite case, and later Gowers in the bipartite case. So the notion of an epsilon quasi-random graph, I'll just say what it is. This is it. That's it. You look at, this is a little bit asymmetric. It depends on, you look at pairs V prime in V. You look at the intersection of the number of edges from V to W. Look at the edges, but from V to W and V prime to W, and look at the look at the W's connected to V and to V prime by some edge. Okay, then it says that the sum of a V prime of that number squared is bounded by a certain number. This is right. So this is polynomially equivalent. Polynomial equivalent means by replacing epsilon by some epsilon to some square or power or something like that. You can, right. So we call two things polynomial equivalent if one is equivalent with epsilon to another one where the second epsilon is epsilon prime is something like some power, fixed power of the first epsilon, maybe a square root or something. Yes. Sorry, Jason, you had a question.
What's delta?
Delta, where delta is, thank you very much. Where delta is the where delta is the density of the original graph. Delta density of the graph VWE, right? So now I can state Semeredi regularity lemma, which is about all finite graphs in a bipartite form. It says, so the question is, can you say anything non-trivial about everything in the world? Can you say something? And this is about all finite bipartite graphs. So you take for every epsilon there's a C, such that for any finite graph VWE, there are partitions of V and W into at most C pieces, such that for each of these pairs, VIWJ, look at the induced subgraph, it's epsilon regular, outside a small exceptional set, which I described there. What's the exceptional set? I. So outside a small exceptional set of vertices, pairs of vertices, all the induced subgraphs in that coming from the partition are epsilon regular. Okay, this is and finding bounds on C has been an important thing, and a lot of people, Gowers, work a lot on this, Semeredi regularity. Okay, this was a big tool in what Semeredi's theorem about arithmetic progressions or something. It was a big tool in that thing. Now, algebraic graph regularity. So So Tao, this comes from Terry Tao. He wrote a paper called Expanding Polynomials ... I think it appeared in some volume. What volume did it appear in? I forget the volume it appeared in. Something maybe for somebody's birthday. Maybe Semeredi, I don't know. Anyway, big paper gave an improved version for bipartite graphs defined uniformly in finite fields. So what it means is equivalently of a given complexity. Okay. an improved version. So you restricted attention to a certain class of bipartite graphs. Okay. And this was a tool. The main point of this paper was a tool in the structure theorem for polynomial maps, P f times f to f as f a finite field, and the polynomial map of a given degree of some kind, right? So there's a dichotomy theorem for these polynomial maps in terms of expanders. And that was but he mentioned that this regularity lemma was interesting in its own right. It should be interesting in its own right. So okay. Here's his algebraic regularity lemma. It's slightly improved by myself and Starchenko and by Hushovsky in terms of he first did it only for when you're finite fields, when the characteristic is getting bigger and bigger, which means in the limit you're in characteristic zero. But it worked with using model theory techniques. We did it. So here's the statement with the improved version. Given a m, there's a c. So there's no epsilon. Just given a m, there's a c, such that for any finite field, and graph VWE definable in f of complexity at most m, which means defined by a formula with parameters, but with at most m symbols, that's what it means. So, yep. By the way, just in passing, in a finite structure, in any language, anything's definable. Everything's definable, right? So it only makes sense to talk about definability with some conditions on. Anyway, right, I lost my drift. So again, given m, there's a c, so for any finite field and graph, VWE definable in f of complexity at most m, there are partitions, again, V into VI, W, WJ, to at most C pieces, where each VI and WJ is also definable of complexity at most C, such that each of these induced subgraphs is this constant times the size of f to the minus a quarter regular. Okay, this was Tau's algebraic regularity lemma. So what's the improvements? Well, of course, the improvement in the conclusion, there's no epsilon. The degree of regularity gets better as the f gets bigger. Okay, and there's no exceptional pairs. This was considered to be the this is Tau's algebraic regularity. Okay, and right, let's now get on to arithmetic regularity. Arithmetic regularity. We now consider this is the arithmetic regularity regime, right? I don't like using the word regime too much for obvious reasons, So anyway, they call it the regularity regime. This is, in this case, you have the objects are now pairs. A finite group with a subset, as I said at the very beginning, distinguished subset, and we try and say something non-trivial about all finite pairs. Is there a similarity regularity lemma, in this arithmetic version, where you say something interesting about all pairs GD. Okay. Now notice that similarity regularity applies to the bipartite graph GG with the edge relations of x y to the minus 1 is in E. So if we think of G as both G and G, it's not symmetric. It need not be abelian. So even then, it's x minus y, not y minus. So it's a bipartite graph. Now, Ben Green wrote a paper, a semi-ready type regularity lemma in abelian groups in this journal GAFFA, which stands for what? Geometric and functional analysis. Is that right? In 2000, he initiated the arithmetic regularity project, but restricted to abelian groups. And his general statement is complicated. It's a very complicated statement, and I don't understand the statement. It's very fully analytic. But restricting, look at a special, but in a special case, there's a fairly clean result. In the special case, you look at consider the case where you restrict the groups to finite dimensional vector spaces over Fp, the finite field Fp, where P is fixed. Okay, just restrict to that context. So the groups are these groups, Fp to the n varying P fixed, and the D is anything, any subset. And it turns out that in this context, semi-radial regularity does apply to the associated bipartite graph in the optimal manner. So if your bipartite graph comes from a pair GD, you could say, well, do you get semi-radial regularity where the pieces are like cosets of some subgroup? This would be a group, a kind of invariant version of semi-radial regularity. And that's what you get, okay? That's the statement. So theorem 0.4 is a special case of Green's theorem, which is easy to say. Fix P and epsilon. Then there's a C such that for any n and any G Fp to the n, the vector space of dimension n over Fp, and any subset of G, there's a subspace H of G of index at most C, such that outside a small exceptional set, as before, with the same properties as before, all cosets V, for all cosets VW of H in G, the corresponding graph VW x minus y in D is epsilon regular. So it gives the optimal, in some sense, in this special case, optimal result. In general, this depends on the fact, actually, that these groups have lots of subgroups. But what if you have something like, what if your groups are FP, additive group FP, as P gets bigger and bigger? There's no subgroups. What do? So in the general theorem, you get what's called Bohr neighborhoods come into the picture. A Bohr neighborhood of a group, say a abelian group, a finite abelian group, a Bohr neighborhood, you look at a representation into S1 to the n, n-dimensional torus, and you take a pre-image of a subset of a neighborhood identity of, say, small diameter. Look at the pre-image, this we call a Bohr neighborhood. They come into the picture in general. Okay? But here, in this case, you get a nice statement not involving Bohr neighborhoods, just subgroups and their cosets. Right. Quasi-random subsets of groups. So Green's statement, actually, the actual statement he makes is in terms of regularity or quasi-randomness of a subset of a finite abelian group. So this notion of quasi-randomness of a subset, which we'll see is connected with quasi-randomness of a corresponding graph. Okay, very much based on bounded Fourier, is connected with Fourier coefficients, Fourier analytic statement. Let's give a definition of quasi-randomness or regularity for possibly non-commutative groups, finite groups, because it'll come into the picture later. So here we take a finite group and a subset of H, and we look at the set of irreducible complex representations of H hat. D is said to be epsilon quasi-random if there's a bound on, for every non-trivial irreducible representation, this phi should be a pi. For every non-trivial pi, you look at the pi sum D and D, pi of D, this will be right, this will be in the corresponding vector space. The operator norm of that is at most epsilon times H. Okay? Yeah, so it's a bound on this size. This is called, so we'll call D as epsilon quasi-random. So it's a Fourier analytic, a non-commutative Fourier analytic version. But it's what's quite interesting. This was worked out actually by Atticus in this non-commutative setting, is that this quasi-randomness of D is closely connected to the quasi-randomness of the corresponding graph. So here you have, so epsilon quasi-randomness of D, in this sense, in this Fourier analytic sense, implies epsilon squared quasi-randomness of the corresponding bipartite graph. Okay, H, X1. And epsilon quasi-randomness of this graph implies epsilon to the quarter randomness of D. quasi-randomness of D. There should be a quasi there, right? There should be a quasi-randomness. So this notion of quasi-randomness for analytic is closely connected with quasi-randomness of the corresponding graph. And maybe I can say, as promised earlier, that for arbitrary graphs, VWE, okay, let's go back to this. Right, I said a couple of slides ago that for graphs, forget about the groups, just for bipartite graphs, there's a notion of regularity, its own regularity, which I gave, which is like separating regularity business. There's a notion of epsilon quasi-random by Chung, Graham, somebody else. And what's the relationship? As a polynomial, well, epsilon quasi-randomness of the bipartite graph implies epsilon to the quarter regularity. And conversely, epsilon regularity implies 12 epsilon quasi-randomness. So there's an interesting relationship between the graph notion and this other. And by the way, this notion quasi-random is actually a technical word. I mean, there are some people who use the word quasi-random to kind of impress other people, you know. Like in a party, you can say, how are you feeling, quasi-random or something. You know, it's a joke, but the word quasi is a technical, it's got a technical meaning. It's not like just to sound fancy. It has a technical meaning, but the idea of quasi-randomness is that random is that something which looks like a random object without being random. So, for example, if this regularity quasi. So, for example, you take the complete bipartite graph. It's not a random graph, but it's quasi-random, right? Because its density of anything is the same density. But density of any induced subgraph is the same. It's one. Likewise for the empty graph. But these are not random objects, but they behave in some sense. They share properties of random objects. Good. Now I can get on to the arithmetic algebraic regularity lemma. Okay. This is what we proved. So what we wanted to do was to do a version of Tao's thing in the arithmetic case. Okay, it was just partly it was something I wanted to do for some time, and it was a project involving maybe with Gabe Conant, who we worked on a lot with, and then we did it. I ended up doing it with thing, anyway. That's it. Here's the statement: for every m, there's a C such that for any finite field F and group G and subset D definable in F of complexity at most m, there's a definable normal subgroup of complexity and index at most C, such that for all cosets V, W of H and G, the associated bipartite graph is again C, the size of F to the minus quarter regular. So it's like semi-radial regularity of the associated graph in the best possible way. Okay, so this is the statement. Okay, so by the relationships above, we also obtain C size of F to the minus a quarter at randomness by changing C a little bit in the conclusion, and then we can actually improve the C size of F to the minus a half quasi-random of what? Of, yes, okay. Then we can improve the conclusion to actually for all G, and one can restate the conclusion in this case as for all G and G, you take the right translate, you have this H, right? You take the right translative D by G for any G, intersect with H, that subset is C, size F to the minus eighth quasi-random in H, in the sense of either of this Fourier analytic sense or the graph theoretic sense. Discussion of the proof. In all the situation, this is a statement about all finite fields, and in all these situations, you prove this by saying, suppose it's false. It means there is an M such there's no C. So you take a bunch of counterexamples. You take, this is a finite fields and things definable of bounded complexity. You go to the logical limit, which means a pseudo-finite field. And you get a counterexample. You get a counterexample by this using a lot of things, using many things. but you have to, yeah. So it's a complicated thing, but it's a somewhat complex. But you have to play with the different counting measures and things like that, and pull things back to the original finite situation. Anyway, why no Bohr neighborhoods? So why there's no Bohr neighborhoods showing up? Because the Bohr compactification, because of the profiniteness of this definable Bohr compactification. That's the reason. And there's a lot of compactness things involved too. So there's no Bohr neighborhoods turn up, as in the general statement. Comments. Now I've got another 5-10 minutes. Let's just make a few comments here. Let's compare to Green's result. Theorem 0.4 was Green's result for the fp to the n, fixed p. Notice that, look at the abelian groups fp to the n, as both p and n vary, these are definable uniformly in finite fields as just the additive group of fq. So the same group is defined. So hence by theorem 0.5, the main theorem, we obtain that given any m, there's a C such that for any p and definable subset D of fp to the n of complexity at most m, there's a subgroup H subspace such that of the corresponding group, such that for all cosets VW of H in F sub p to the n, the corresponding bipartite graph is C over p to the n over 4 regular. So that's it. And the improvement in the conclusion over Green is no exceptional, it's just like no exceptional pairs, no epsilon. The degree of regularity improves, the field gets larger, and we also have uniformity in P. So in the special case of the Green's theorem, you get actually a very nice, and of course at the expense of D being defined uniformly. That's the. So this is analogous to the relation of Tau's algebraic graph regularity to similarity graph regularity. Okay. Now, from a result of Rashevsky and me from 90s, the groups defined uniformly in finite fields are essentially the form G of F for G an algebraic group over F of bounded complexity. So those are, the definable groups are more or less algebraic groups up to finite index, something like that, and but they're essentially algebraic F points of algebraic groups. Of course, as I said, take any finite structure, anything's definable. But we're talking about defined uniformly as the fixed formula as the field varies. They're basically algebraic groups. It's because the defined groups in pseudo-finite fields are of this form. And you pull it down to the finite field. Now, at the other extreme from commutative algebraic groups, so the additive, we studied before the additive group. That was the case before. That's a commutative algebraic group. But at the other extreme are semi-simple algebraic groups, which I want to say something about. And this is what we learned more recently. And I talked about this in the other things, and I didn't say something completely right. So take a semi-simple algebraic group. This is in the sense of algebraic group theory. They always have universal cover. So these are connected semi-simple group. Semi-simple group means it has no infinite, no normal, connected, non-trivial abelian subgroup. That's what it means to be semi-simple. Connected, I mean, as an algebraic subgroup. And they always have universal cover. Universal cover is a connected, so-called simply connected algebraic, semi-simple algebraic group mapping onto G with finite kernel. And simply connected means you cannot have a proper cover of that. There's a maximal such cover, which has a finite kernel. Okay, so it's they call it universal cover, but in the algebraic group category. Now, you take simply a connected algebraic group without necessarily simple of bounded complexity over a sufficiently large finite field, then in fact, the F points of G will have no definable subgroups of index and complexity bounded by M. So what this means is if you take a pseudo-finite field and a simply connected algebraic group over that field, look at the F points, it's connected as a definable group. It has no definable finite index subgroups. That's the reflection. So this was also proved by Rashevsky and myself. So theorem 0.5 applies to this to give a C such that for such a group G, for a definable subset D of GF of complexity at most M, already D is C F size of F minus 1/8 quasi-random without finding a because you can't pass to a subgroup of bounded complexity and index. But so this we said, okay, we do something, but in fact, much more is known, and let me say what more is known. In the semi-simple case, a stronger result is already present. Can I have until 4:30? Is that okay if I have until 4:30? Do you mind? Or should you want me to stop earlier? Yeah, I should be able to finish everything. In the semi-simple case, a stronger result is present in essential literature, based in the literature. And here it is. Given D, there's a C, such that for any finite field F and connected, simply connected, semi-simple algebraic group F G over F of dimension at most D, every subset of GF is C size F to the minus 1 quasi-random. Every subset. Okay? So this is a stronger result, much stronger result. So what's going on here? So the point, what's the point? The point is that the conclusion is bound up with a minimal degree, I'll call M of G of F, of an irreducible complex representation of G of F, which means that you have this degree. It means every subset of GF will be 1 over the square root of MGF quasi-random. This is in the case of simple algebraic group. It doesn't mean that there's no. There could be a center, but there could be a center, but it's finite. But you take and for simple algebraic groups over F, this is a result of Seitz and somebody Landau, which I'll mention in a second. The point is that actually, the point is that if you take a simply connected semi-simple algebraic group over F, look at the F points, then the F points will be a product. So semi-simple group is always an almost direct product of simple algebraic groups. It's not going to be the same for the F points. The product will be a finite index subgroup. But in the simply connected case, it's the same. So the point is that, what's the point is that the assumptions imply that GF is an almost direct product of GIF for GI almost simple algebraic groups, and then you can apply the results of Landau and Landau. So whereby the M of GF is MGI for some I, and the case of MGI is done by Landau and Seitz. So there's a much stronger result available for semi-simple groups. And let's expand in the last few minutes a bit on this. If there's time, there's a bit of time. Okay, so it's not uninteresting. This material is taken from Briard's Lectures on Approximate Subgroups, which is a nice, it's funny, he's got this survey paper, 2011, very nice paper, but it doesn't mention what, so Żurawski also worked on approximate subgroups. It's some very nice things which have influenced everything we're doing, but it doesn't take account of Żurawski's work, which was done actually earlier, but it's a very nice survey paper. I think it's based on some lectures somewhere, IHES or Lumini. So Gauss defined a finite group to be epsilon quasi-random if every subset is epsilon quasi-random. Okay? Gauss. As above, if M of G is the minimal degree of an irreducible complex representation, then it's a fact by using the full analytic analysis that G is 1 over square root of MG quasi-random. By the way, when G is abelian, this minimal representation is 1. Well, if G is an abelian group, the minimal degree of a irreducible representation is 1, S1. But abelian case, so MG is 1. It says nothing for abelian groups. Now, there's a thing called Jordan's theorem. So Jordan's theorem says that you fix n, it says there's a function, right? There's a function f, increasing function n to n, such that if you fix given n and you take g in GL n C finite, then it has a normal abelian subgroup of index at most Fn. This is Jordan theorem. So if you fix n, then any finite subgroup of GLNC has a bounded index, depending on n, normal subgroup, which is abelian. Okay? And this tells you straight that a non-abelian finite simple group is epsilon random, with epsilon going to 0, the size of G gets bigger. Okay, together with this representation business. Okay, and the fact about the quasi-randomness, depending on and the connection with the representation. So in fact, via Jordan's theorem, so we've been working for a long time, since 2018. So I worked actually with Gabe Collins and Caroline Terry on an arithmetic regularity in a stable context, actually. Since then, we want to do the general arithmetic regularity as in green, but for arbitrary groups, not so abelian groups. But via Jordan's theorem, we expect some kind of reduction to a close connection with the abelian case for a general arithmetic regularity lemma for arbitrary finite groups, which is in progress with Gabe and Collins and Caroline Terry. So, right, so yes, that's it. So I think I said thanks very much. Bye-bye. Just sorry, normally I'm relaxed, but I'm a bit stressed today for some reason. Sorry. Anyway, yes.
We just, so in this last point, make some